All right, so we are continuing section 8.3, and now we want to be able to estimate when a series converges, we want to be able to estimate its sum. So here, let's remember what we have here, and let me see. Let me just change that font a little bit. I don't know why they have it so fat to begin with, but that's fine. So here is the general form of our series. And we're going to call that series S. Okay? And the S sub n is the partial sum of the first n terms of the series. First n terms. That's now assuming that n started with n equals 1. Obviously, if n starts at a different number, like 2 or 3 or 4, you have to just then make the appropriate adjustments in your mind. So if we approximate the infinite series sum with this nth partial sum, the difference between the series sum and the nth partial sum, its estimate, is defined as R sub n. So another way to think about R sub n, I'll maybe put it up here. R sub n is equal to the value of the series minus the nth partial sum. So S sub n, again, is the nth partial sum, which is the sum of the first n terms of the series. This here, the summation, the sum, that's your infinite series. That's your infinite series sum. Okay. And I'll make a few more notes here. The nth partial sum is an estimate. The infinite series sum, right? The infinite series sum, that's the truth, right? That's the truth. That's, so to speak. That's the true value. Maybe I should say the true value instead of truth. That's probably a little better. Okay, hang on. Okay, so this is the true value. Let me get a little bit of this. You have to forgive the background noise. Okay, and this R sub n is known as the remainder. Okay, so the difference between the true value of the series and its estimate, which would be the sum of the first n terms of the series, that difference is called your remainder, R sub n. And oftentimes, I mean, if we're gonna estimate the sum of our series with the nth partial sum here, we'll get an estimate, but we'd like to know how good it is. Well, understanding what the remainder or the error is in the estimate, or getting an idea of what that is very important. And we have in section 8.3 what's called the remainder estimate for the integral test. One moment. Okay, so let's do a problem dealing with this. So, well, no, first of all, let me bring up the ebook. Let me bring up the ebook. One moment. Hold on, everybody. Let me see. One moment, everybody. Give me a moment. I'll find it. I probably should have. It's right before example 6. All right, so let me bring up the ebook. So that remainder, the S, is the infinite series. That's what the S is. And this is the remainder estimate for the integral test. So what they're doing is the remainder, the R sub n, which, remember, the remainder R sub n is the error when you approximate an infinite series sum with an nth partial sum. That remainder is between two values. It's bounded between a value on the left and a value on the right based on this remainder estimate. The value on the left, the integral, which is the improper integral from starting at n plus 1, n plus 1 to infinity of f of x dx. That's the lower bound, and the upper bound on the remainder is the integral from n to infinity of f of x dx. So certainly the upper bound is more important than the lower bound. Okay, we'd like to know how much, like what's the upper bound on the remainder? In other words, the error using our nth partial sum to estimate the infinite series is no more than this value. Okay, that, for example. So let's look at an example here. I got one worked out. Okay, I have one worked out here. And it's well, let me give you a moment to copy this down. One moment. Okay, so this series here, now what kind of series is this? What kind of series is this?
Harmonic.
Well, let me ask you this, and I appreciate all responses. It's certainly a P series. That's right, Jonathan. Is it a harmonic series? A harmonic series, harmonic. It's not geometric. P series is not a geometric series. Geometric series and P series are different types of series. It's not a telescoping series either. It's a P series. This is a P series. So I appreciate all the responses. This is a P series with P equal to what? Good, Jonathan. Good, Clay. P equals 4. And since P equals 4 is greater than 1, this series does what? This series, does it converge or diverge? It converges indeed.
Converge.
Okay. Now, a harmonic series is a P series, but with n equals 1, P equals 1. And that series diverges. Just so I thought I'd just mention that. But we don't have a harmonic series here. We don't have a harmonic series here. We have a P series with P equals 4, and it converges. And since the P series converges, it makes sense that we would want to estimate the series. We would never be interested in estimating a series that diverges, but if a series converges, it makes sense to try to estimate the series. So, okay, what we're going to do is we're going to utilize the remainder estimate for the integral test. So on that note, if we're good here, let me go to the solution and let's talk it through here. Are there any questions before I move forward to the solution? Okay. Now, first of all, I want to just note here, I want to note that so that your term in your series, your term is, gosh, hold on, to erase this. Hold on, we'll get it. Your term in your series, the A sub n, okay, is 1 over n to the 4th. So in terms of the function that corresponds to that, the function would be 1 over x to the 4th. And that's a continuous positive and decreasing over the interval from 1 to infinity. And because of that, the integral test applies. We're not going to use the integral test. We're not going to use the integral test on a series that diverges. This series converges because by the integral test, this series converges because the corresponding function, which is 1 over x to the 4th, is continuous, positive, and decreasing over the interval from 1 to infinity. And so by the integral test, this series converges. But also, the series converges because it's a P series with P equals 4, which is greater than 1. So, okay, what do we want to do now? All right, we know by the remainder, by the remainder estimate for the integral test, okay, we know by that theorem, which is it comes before example 6 in section 8.3, that the remainder has to be has to be less than or equal to the integral from n to infinity of 1 over x to the fourth dx. So I can get an upper bound on my remainder, which is, again, the error in approximating the infinite series using a partial sum with n terms, okay, the first n terms of the series. The remainder for the partial sum estimate to the infinite series is less than or equal to the integral from n to infinity of 1 over x to the fourth dx. And now this is just like section 5.10. How many remember finding improper integrals? You know, why is the integral improper? Because there's an infinity in one of the limits, right? And so we have to write the integral as the limit as t goes, but we have to replace the infinity with t, and then write the integral as the limit as t goes to infinity. Okay, how many remember this from their improper integrals, section 5.10 that they studied? It's been a while, but how many recall it? Okay, Yonatan remembers it. Oh, surely some others of you remember improper integrals, right? How about a few more thumbs up on that? Okay, Clea remembers it. Avery remembers it. Okay, all right. So, well, the antiderivative of x to the negative fourth is x to the negative third over negative 3. I can factor out a negative third. And then I'm going to be looking at the limit, negative 1/3 times the limit as t approaches infinity of 1 over t cubed minus 1 over n cubed. Well, the 1 over t cubed is just, I mean, this is going to just equal, this is just going to equal 1, when we take the limit, 1/3 times 0 minus 1 over n cubed, right? And that's going to give us then 1 over 3n squared. So this means then that the remainder is less than or equal to 1 over 3n cubed. The remainder is less than or equal to 1 over 3n cubed. Now in our problem, are there any questions on that? All right, well, in our problem, we want to estimate the series correct to 2 decimal places. This means that we want to set our 1 over 3n cubed to be less than or equal to 5 over 10 cubed. So because we want correct to 2 decimal places, we have to take the remainder and make it less than or equal to some bound that will ensure that we're correct to within 2 decimal places. Well, the reason we have 10 cubed on the bottom is because, well, I mean, what's 5 over 10 cubed? 5 over 10 cubed is 0.005. If your remainder is assured to be less than 0.005, then you won't, like, round off will not affect the first 2 decimal places. So that's why you have 5 over 10 cubed. If you had a situation where you wanted, like, for instance, correct to 3 decimal places, or let's say 4, correct to 4 decimal places. Okay. In that situation, if you wanted your estimate to be correct to 4 decimal places, then your remainder would be less than or equal to, you would set it less than or equal to 5 over 10 to the what power? if you want accuracy to within 4 decimal places. What would it be, Yonatan?
Where
5
did
over
we
10.
get where did we get the 5 over 10 cubed from? Like I understand why you want 10 cubed, that way you can get decimal places, but where'd you get the 5 from?
Well, and on that note, so here we would want 10 to the 5th power here, if we want to correct to 4 decimal places. The reason you have a 5 in the top has to do to rounding. You don't want rounding in the 3rd decimal place to affect the first 2 decimal places. So that's why you have a 5 there.
Okay, thank you.
Okay, all right, good question. Good question. So it's always going to be like there on the left there, correct to 4 decimal places. You would want 5 over 10 to the 5th power. So 5 is always going to be in the numerator, and then the denominator will be 10 to the appropriate power. So we need to solve for n now. To estimate the series, we need to figure out how many terms of the series do we need to use. So we're going to find that by solving this inequality here, right? We're going to do that by solving this inequality. So let me just clear the annotations here. So what we can do, of course, is let me see here. So I mean, I know what I did, but what I did here was I multiplied by 3n cubed on the left and the right. That doesn't change the inequality. The inequality is still less than or equal to. Why did the inequality not get changed when we multiplied both sides of the inequality by 3n cubed? Why did that not change?
Because we don't have a negative number. If we had the negative number, we would.
That's right, Clea. Very good. N is going to be some positive integer, right? N is how many terms in the series are you using? So it's a positive integer. So whatever 3n cubed is, it's not going to be negative. All right, you multiply through, you get 1 less than or equal to 15n cubed over 1,000. And then you can multiply here this inequality by 1,000 over 15. And so you're going to get n cubed is greater than or equal to 1,000 over 15. Okay, and so are there any questions before I go to the next page? All right, well, we have to solve this inequality here, so I'll go to the next page. So n cubed is greater than or equal to 1,000 over 15. And what I'll do, maybe I'll put in a step over here. So n cubed is greater than or equal to 1,000 over 15. Hold on here, I like work to be very clear. I'm seeing some very nice work, by the way, in the work that you're submitting to me for the exams for parts 1 and 2. All right, so n is greater than or equal to 1,000 fifteenths to the 3rd power. Well, that's just the cube root of 1,000 fifteenths. And if you work that out, you're going to get that n is greater than or equal to 4.0548. And so you're going to need, algebraically, you need 4.0548 terms. Well, that means then you're going to need 5 terms, right? Because you need more than 4. You need more than 4. So, okay, we need 5 terms. And what I do now is, okay, here's my series. Here it is. And I'm gonna write down the first 5 terms of the series and add them. And that's my 5th partial sum. 5th partial sum is equal to 1.08035195. Is that correct to 2 decimal places? Well, what you can do is you can find the 6th partial sum. Okay, the 6th partial sum, right? If I were to do the 6th partial sum, is just, 1 over 1 to the 4th plus 1 over 2 to the 4th. I don't know why that's plus 1 over 3 to the 4th plus 1 over 4 to the 4th plus 1 over 5 to the 4th plus 1 over 6 to the 4th, right? And if you compute that, I want to make this look nice, class. If you compute that, you're going to get 1.0811235534. And you see the first 2 decimal places agree. You get 1.08. In other words, the first 2 decimal places, the tenths and hundredths place, remain 0.08. So you see, this just shows that if you add more terms to the series, like the 6th partial sum is 1 more term. If you take the 5th partial sum and you add another term, and that would be the 6th partial sum, you add another term to the series, you get the 6th partial sum. That 6th partial sum, the tenths and hundredths place do not change. So this shows you that basically adding more terms to the series will not change the first and second decimal place. And so our series is approximately equal to 1.08, and that's assured to be correct to 2 decimal places. See that? How many think that's, so we have an estimate of our sum. We have an estimate. Now it's only correct to 2 decimal places, but if you're happy with that, you only needed to add 5 terms of the series. If you want the series to be correct to more decimal places, well, then you have to add more terms of the series, right? To get more accuracy, you have to add up more terms of the series. And in the homework you'll have some help aids too, but this is, I think, a pretty good presentation for the remainder estimate for the integral test. And actually, too, I'll mention example 6 in the book, example 6 in your textbook. I would recommend you look at that example as well, okay, for this kind of problem, remainder estimate for the integral test. Are there any questions before I stop the recording? Incidentally, how many think just this is, we have some computer science majors in here. How many think from a computer science perspective, this is interesting? So I was hoping maybe I'd get 1 or 2 people to All right, Yonatan. Yonatan says he's not quite comfortable yet with the material, but he finds it interesting. I'll accept that. I like that. All right, are there any questions before I stop the recording? Okay, I'll stop the recording. Thank you. And we're done with, this is section 8.3. Excellent.